One of the things that we did not note previously, and that is worth noting, and it's important, is that we were dealing with the mean and variance covariance matrix that were part of what we call a population. So imagine, and the population doesn't have to be of people. That's the important thing. It's whatever we are sampling from. So it could be that we have maybe a bunch of machines, and we're taking some measurements on how maybe bottles of some soda are filled up, and we can't look at all of them and measure exactly how much is in every single bottle, but we randomly sample some from the assembly line, and here is our population, and from there we get some subset of that, which we'll call our sample. So we'll have little n elements that will go into our sample, and then our population will have capital N elements. It's, of course, important to note that n has to be less than or equal to capital N. So you can't obviously draw your entire, more than your entire population, but you can draw up to your entire population. So rarely are we ever dealing with populations in data science. Usually we're dealing with samples from there because it's just unfeasible to draw an entire population. So for our population, we discovered that we could end up with the mean vector, which would be the expected value of our x vector. And then we could get this thing called the variance covariance matrix. So here I'm just going to refer to this as a d by d to distinguish it from the sigma means to add up. Here this is a matrix, here this means to add up. I know I don't like it either, but it's just the way it is. Now when we draw our sample of n elements here, in our sample we want to approximate the true population. We want to get a sense of what that is. And so what we do is we instead compute what's called x bar. Now this is going to be a vector of means, and I'm sorry, not x vector, but oops. Not the entire vector, but the x, we'll denote that with an x and a bar over it. That is a vector of means. And that will simply be the, just like we would compute a normal average, but it'll be based on those n observations. So we'll add up the n x's that we collected from the population of capital N observations, and then of course we'll divide that by little n, since that's how many values we have in there. Also, instead of calculating sigma, which we often don't know, we'll compute the S matrix. Now S and sigma are the same letter if you think about it. Sigma is Greek, right? And the way that we'll treat those differently, you might say, well, that's probably just going to be 1 over little n times the deviations squared. Now keep in mind that we're not actually squaring the deviations. Here what we have is we have a vector of observations subtracted away from the mean vector, but it's not squared because we're dealing with vectors here. So the way we square something is we multiply by its transpose. Okay, so we could think about this maybe as person 1's vector of data. So maybe they have 3 pieces of data, and then we figure out how far their pieces of data deviate from the mean vector, and that's what this x sub n minus x bar means. This is for each person, if you will, and this is the average of all the people if our sampling units are individuals. And so instead of dividing those deviations squared, right, that's what we'll get when we multiply that by the transpose. We'll get the square of those values. And we're not going to average them by dividing by n. We're going to divide by n minus 1. Now, the reason we do this is because we want to approximate the sigma matrix. And this has to do with statistical theory, but we want it to be the case that the expected value of our sample variance covariance matrix, that it's on average going to give us the sigma matrix. And what does that mean? Well, that means that if you were to sample repeatedly from this population and you were to average them all together to get the sigma matrix, well, you would have to divide by n minus 1 instead of n. That's all we need to worry about here. But just keep in mind the distinction is we have a population, mu and sigma, but we're going to approximate those with x bar and s. Now, it's also important that when we're working with random variables, oftentimes we're going to be combining them in some way. So say we have two random variables, x and y, that are characterized by the states x vector and y vector, and they are going to be d by 1 vectors. Okay, each of these will be d by 1 vectors. This has to be the case because otherwise you can't add those vectors if they're not the same size. So you have these two random variables, and the expected value of their sum is the sum of their expected values. Convenient, because that just means that the expectation is a linear operator. Okay, these two really do the same thing. One's just addition and one's subtraction. And expectation is a linear operator. So just like a derivative, if you take the derivative of a sum, it's the sum of the derivatives. It's not quite distributive property, but a lot of people like to think about it that way. Now the variance becomes a little more interesting. The variance of a sum or difference is the sum of the variances. So you can see that up to here, it's very similar to the expected value result, but then you actually have to add these or subtract these two covariance terms. For the variance of x plus y, you have plus the covariance of xy plus the covariance of yx. Now it's important to note that these are not the same. Remember, the covariance is a matrix, and if you put the covariance of xy, then you'll have the labels here will be x1 through xd, and the labels here will be y1 through yd, versus when you look at this one, the labels will be y1 through yd and x1 through xd, like this. And so when you add these two, you're not necessarily adding the same components, because, well, you think about it down here, you'll have ydx1, but here you have xdy1, and those are very distinct. Some of the entries may be the same, like x1y1 and y1x1 will be the same, but they won't be entirely the same. The only difference between the subtractions is the signs, right? All right, let's see how we could actually implement this. There are a lot of times where we will take combinations of random variables. In this case, let's say that y is a linear combination of x. So it's going to be some matrix A times x plus some vector b. So ax equals ax plus b. And that's just a linear operation there. So how would we compute the expected value of y? Well, that would be the expected value of, let's replace y with ax plus b. Now, if you distribute that across, because we know that this distributes, you would get the expected value of ax plus the expected value of b. Now the thing is, a and b are constant matrices in vector, and so they on average are themselves, right? They're always the same. So what I can actually do here is I can factor out the A matrix, and it will be the expected value of x, because A itself is just a matrix of constants. And same thing with B, it's just a vector of constants, so its expected value will be itself. And so expected value of x is what we call mu, the mu vector, plus b. And so the expectation of that will be a mu plus b. What about the variance? Well, variance of y would be the, and I just abbreviated this v, sometimes you will see that. The variance of y is the variance of ax plus b. Now, what do we know about the variance of a sum? Well, it's going to be the variance of x. So in this case, the first term, variance of ax plus the variance of b plus the covariance between ax and b plus the covariance between b and ax. All we're doing here is we're just unpacking the definition. What we're calling quote-unquote x here is the ax, and what we're calling quote-unquote y here is the vector b. Now, the good about this is that variance has to be applied, or covariance has to be applied to a random variable. So in the case of the vector b, that's just a constant vector. So if I ask you, what is the variance of a constant? And well, it's constant, right? It's not changing. And so that means that it doesn't have any variability. So this would be, the variance of this would be zero. Now this is actually a matrix of zeros. So keep that in mind because it's a variance of a vector. Now similarly here, if you look at the covariance, okay, this does have a random variable in it, but by what amount does a random variable vary with a constant? Well, they don't covary, right? They don't vary together. So there's a zero covariance there, and similarly, zero covariance here. So what we end up with is the variance of ax. And in this realization, there are two more properties that might be helpful to have here. What do you do when you have the variance of a multiple of a random variable? Well, if this is just some constant, so c is just some real number, it's just one number, then the variance of that would be the square of that constant times the variance of the random variable. So the idea here is just that we are able to always express the variance in terms of variance of the random variable itself. Now, if that is a matrix, so A is a matrix, I'm not going to worry about dimensions here so much. If A is a matrix, well then how do you deal with the variance of A times a matrix? Well, it's kind of the square of the matrix, but the way we do that is by having A and as a pre-multiplier and A transpose as a post-multiplier. So in our case, this will be A times the variance of X times A transpose. Now, the variance of X is the sigma matrix. It's the variance covariance matrix. Sometimes you call it the variance matrix or the covariance matrix, but it simplifies down to this, A sigma A transpose. Now, what about the covariance between X and Y? Well, that is equal to the covariance between X and A X plus B. Looking back, the covariance between two random variables is the expectation between one random variable and the transpose of the other minus the expected value of the first random variable times the expected value of the transpose of the other. So we're going to use that to break this up. Remember, our goal here is just to get it in terms of things that we already know. And so the covariance here will be the expected value of X times the transpose of the other quantity there minus the expected value of X times the expected value of AX plus B transposed. So notice that we've applied exactly that. Expected value of the first times the transpose of the other minus the product of the expected values, second component being transposed. All right, so in this first one, we can simplify this further because remember, we're trying to get it in terms of the expected value of x. So if I distribute that across, the transpose of a sum will be the sum of the transposes. So here's what this will break down to. This can become AX quantity transposed plus B transposed. And then hopefully that's intuitive that you can do that. And I'll show you why that should be intuitive. If you think about adding together two quantities, like let's say two vectors, 2, 1 plus 3, 1, but you want to transpose that result. So if you added them together first, you get 5, 2, and if you transpose that, you'd get 5, 2 as a row vector. But if you transpose them first and added 2, 1 plus 3, 1, notice now you're just adding two row vectors and you'd get 5, 2, which would be the same thing. So that's really all we're doing here. And now over here we have minus, that's mu, is expected value of x. And then here again we can apply that same notion of the expected value of AX transposed plus B transposed. Okay, now if we can deal with this AX, the transpose of AX, there is a property from linear algebra that's helpful here, that if you have a product of two matrices transposed, that equals the product of the transpose in reverse order. So we have to use, it's helpful to use this, I should say, and that will give us the expected value of vector x times x transpose times A transpose plus B transpose. Okay, so all we did there is just took the transpose of AX, which according to this property would give us X transpose A transpose. And now we can go ahead and deal with the other terms here. So minus mu times, this will be the expected value of X transpose. I'm getting my vector signs there. Times A transpose plus B transpose. Now and remember mu is a vector, so I should have written this as a vector. I did leave off, here's this X, I didn't distribute that all the way across. So let me come back and adjust that. So that X vector should distribute to the B transpose. So we have plus X times B vector transpose. Okay, now we could use the linearity of the expectation. And so in the first term, we'll get the expected value of this quantity here. Use a different color for this. We have the expectation of this quantity here. Okay, and that will be the expected value of X times X transpose. Now keep in mind A transpose is a constant with respect to the random variable. I can't pull it out to the front because then I'd be changing the order of multiplication. So I'll have to factor it out to the right. And then I will have plus the expected value of XB transpose. And once again, what I can do there is it's the expected value of X times B transpose. Again, I have to factor it to the right. It's a constant, but I can't factor it to the left because I'd be changing the order of multiplication. Okay, now you can do this similar process here, and let's go to say orange. So we'll have the expected value of that. Remember, we have minus mu times that, so we'll have to distribute it in. So we'll have minus mu times the expected value of X vector transposed Again, factor out to the right that A transpose, and now do the same thing with B transpose. We'll have minus mu times the expected value of B transpose, which B transpose is a constant with respect to X, so the expected value of B transpose will just be B transpose. Now we can do a little bit of cleaning up. By the way, note that the expected value of X right here, this is equal to the mu vector. Again, I should be using vector notation here. I'm getting a little bit sloppy. These two terms will cancel out because notice they are the same. And here I will have the, and by the way, also here, I should point out that this is expected value of X transpose is mu transposed. It's just the average of these X values, but laid on its side. And so here we'll have mu times mu transpose and multiplied by A transpose. Now, if I, from these two terms, I see that what I have here is the expected value of X times X transpose. What I'm going to do is I'm going to factor out from both of these terms. I'm going to factor out to the right this A transpose term, and then I'll have minus mu, which I'm going to rewrite this again as the expected value of X, and this will be times the expected value of X transpose. And by definition, this quantity here is the sigma matrix multiplied by A transpose. And there we go. So the covariance between X and Y when Y is equal to AX plus B is the standard variance covariance matrix multiplied by A transpose. So the value of that vector B did not make any difference. All right, last thing in this particular topic is let's revisit the idea of independent random variables again. Now just applying them to vectors. So the probability of a y vector, given what we know about x, if these two events are independent, then that knowledge about x vector will not change the probability of y if they are independent. And therefore, that should just be the probability of y without worrying about the condition x. Similarly, the probability of x given y, if x and y are independent, should just be the probability of x. A couple of really useful and handy things. When we have independence, there is no covariance. If two random variables are independent from one another, they behave independently, well, then they have zero covariance. They do not vary together. And so notice that the variance of the sum does not have the plus covariance of xy and plus covariance of yx. And that brings us to this last one here, that the covariance between two independent variables will be the zero matrix. These properties really apply to what we want to do in machine learning, which is we want to be working with what we call independent, identically distributed random variables. So what that means is that the random variables are independent. They, have the probability of one is not influenced by knowledge of the other. And we also want to have our random variables be identically distributed, meaning that if x follows a uniform distribution, we also want y to follow a uniform distribution.